than average, I think, to learn an important computation rule related to the derivatives of functions of several variables, namely the chain rule. When we speak about the chain rule in this section, we're talking about the chain rule for functions of several variables, as I mentioned here. So let's review briefly from Calculus 1 what the chain rule is all about. So from Calculus 1, when you deal only with functions of a single variable, remember that the so-called chain rule is essentially a rule for differentiating the composition of two functions. So if you have f of g of x and you want to differentiate it, then you basically differentiate the external function, so to speak, keeping the inner function as a variable, and then you multiply by the derivative of the inner function, g prime of x. Using the differential notation, so if I say that, let's say y depends on x, and then in turn x depends on t. So in other words, let's say, y is a function of x, and then in turn x is a function of t. Then you can compute the derivative of y with respect to t by differentiating y with respect to x first, and then multiplying this with the derivative of x with respect to t. In particular, this last format of the chain rule from Calculus 1 is going to be relevant for today. So I find that it's not practical to let me see, there's some little bit of a glitch here. So that f didn't show up on f of g of x. So it's not worthwhile, in my opinion, to go over the proof of the chain rule for functions of several variables. I mean, it's not overly difficult, but it's more to write than I would like to. So I'm going to just focus on this in this section on just the computational aspect of it. So I'd like to think of two rules. I mean, I separate them just because of a little bit of a notation aspect to it, although it's really the same chain rule. So the first type of chain rule for a function of several variables is when you have a function, let's call it z equals f of xy, and then in turn x and y are functions of t. Let's say x is g of t, some function of t, and y is some function of t, h of t. Or you can just say x equals x of t, y equals y of t. We're going to use the differential notation, so we're not going to have to rename them g of t, h of t. So just like this version from Calculus 1 with the differential notation, we can essentially create now a tree of dependence in which at the root is f, the function, the most external function, and then with arrows, more than one, right, because we're talking about a function of several variables, we indicate the dependence of f by those variables. Could be 2, 3, or more, depending on the case. And then in this type 1 that I want to go over, all of these variables in turn depend on another variable t. So if I want to find the derivative of the composition, in this case df dt, because see, this is the notation here with the differential notation, you can view the function f as a single variable function, right, via x of t and y of t. So, f of xy is a function of several variables, but if you replace x and y with their respective functions of t, with something in terms of t, you can think of this as a single variable function. And that's the reason why when I compute the derivative of f with respect to t, I'm going to use the differential notation here, df dt. I think I forgot to mute this one. Sorry about that. Okay, so df dt. As opposed to partial f partial t, that's what I'm trying to say here, right? I mean, because whenever you refer to a derivative of a function of several variables, then you would use the partial notation. So going back to the chain rule, how do you compute this? Well, this is just a combination of Calculus 1 chain rules, basically, over all paths of dependence from f to t. So to be more precise, because f depends on t via x, df dt is going to be df dx, excuse me, let me start over here. So df dt is going to be partial f partial x, right, because f is a function of two variables in terms of x and y, multiplied by dx dt. And then you add all the other possible paths. So for example, in this case, f depends on y, and then y depends on t. So you're going to continue with df partial f partial y dy dt. You don't have to make these circles here on the tree of dependence. I just do it once so you can see what we're talking about here. So in other words, when you compute the composition, the chain rule for a composition or function of several variables, you basically add all the chain rules via all these possible branches of dependence via the several variables of f, right? So in other words, for example, if you have, let's say, f depends on three variables, x, y, and z, and in turn, each three of them depend on a variable t, again, df dt is going to be partial f partial x dx dt plus partial f partial y dy dt, and then finally partial f partial z dz dt. So we should actually go over an example right away just to see how this works. So suppose f of xy is equal to the function xy third minus x squared y. And then in turn, x depends on t by x equals square root of t, y equals t squared plus 1. So for example, this could be a motion in space. Let's say you have a motion described by this curve on the surface given by f of xy. And let's say the question is to find the dependence of f with respect to t at the point t equals 1. And like with all problems related to this type of questions, again, you will have to compute the derivative first. We're going to do that carefully, and then we're going to worry about plugging in the value t equals 1. So once again, f depends on t via x and y. And then that means, according to the chain rule, df dt is partial f partial x dx dt plus partial f partial y dy dt. And we're going to compute carefully now each of these. So the partial f partial x, that's going to be y third minus 2xy multiplied by dx dt, which is 1 over 2 square root of t. And then plus partial f partial y, which is 3xy squared minus x squared, and then dy dt, which is 2t. So notice that, again, this is actually a function of t, because remember, at this point, I could substitute y with t squared plus 1 and x with square root of t. We don't do that actually in practice that often. It's not really necessary to write everything explicitly in terms of t for a very practical reason. So first of all, once I know what x and y is in terms of t, I can just basically save it and then keep it like that so that I don't have to write a more complicated expression, right? It will be tedious to just substitute these function in terms of t. And then secondly, if I have to compute the derivative at a specific point, like in this case at t equals 1, I'm going to evaluate x and y at t equals 1 and plug in the actual values. But you have to be careful to make sure you plug in the correct values in the correct variables, right? So when t equals 1, you go all the way back to the dependence of t of x and y, and then see which are the corresponding values of x. So x equals square root of 1, which is 1, and y equals 1 squared plus 1, which is 2. So you're going to replace x with 1, y with 2, and x with and t with 1 in the derivative that I have to compute. So df dt at the point t equals 1, so at t equals 1, is going to be y third, which is 2/3 minus 2 times 1 times 2, 1 over 2 square root of 1, 3 times 1, y squared becomes again 2 squared minus x squared, which is 1 squared, times 2t, which is 2 times 1. All right, so do the computation yourself, and then check that this whole thing should be equal to 24. 8 minus 4 to 12, 22, okay, 24. So that is the derivative at that point. So the second version is basically more of the same, roughly speaking. We're going to do actually more than one example, like we're going to do 2 examples. But the only distinction is that everything is a function of at least 2 variables. So that means in this rule we established here, we're going to use the partial notation, and there are as many chain rules as you can apply for as many variables you have in the last level of this dependence tree, right? When you look at how a function depends via other functions. So I think it's probably worthwhile to yeah, actually, let's actually establish the rule here, and then we're going to save the next page for examples. And yeah, let's just write the rule here, and then we're gonna repeat it on the second page. So, by the way, the number of variables doesn't matter. It could be 2, 3, 5, whatever, but the rule is the same. However, for practical purposes, we're gonna again choose functions of 2 variables, because otherwise we can expand this tree too much and it will be very tedious. So let's say f depends on, I keep on having this software reminder. So let's say we have f depending on x and y, and then in turn x and y depends on s and t. Right? So each of them is a function of 2 variables. So I could ask via this composition, I could ask 2 partials to compute. Partial f partial s, partial f partial t. And by the way, if x in turns would depend on 3 variables, not 2, of course you could ask 3 chain rules, because you could compute 3 partial derivatives, right? I mean, if you had 3 variables in the end. So the rule is really the same as before. You go over a combination of calculus 1 chain rules, basically, by looking at all possible paths of dependence. So for example, in how many ways, I mean, how does f depends on s? Well, it depends on s via x, and it depends on s via y. And according to the rule, then partial f partial s is going to be partial f partial x times partial x partial s plus partial f partial y and then partial y partial s. And it's important to remark here to notice that on the second step, I'm not going to mess up this picture one more time, but you get the drill. On the second step, you don't have to compute again the partial x partial y. These were computed on the previous step if you have to do both of them. So how many ways can f depend on t? Well, it depends on x first, then x depends on t. I don't want to say partial too many times because I have a tongue fracture if I do that. So partial f partial y, and then partial y partial z, partial y partial t, sorry, right? So y depends on t. So we're going to go over an example on the next page. Let me just write it here, and then you can pause the video and try to do it on your own, and then check with me when we turn the page. Let's say z equals depends on is ln of 3x plus 2y, and in turn x is s sine of s times sine of t, and then y is t cosine of s. All right, so let's stay tuned for the second page. All right, so actually let's say we want to compute as a question here. Okay, let's say we want to compute the derivative with respect to s and t for z at the point 0 pi. So obviously this refers to s and t. You have to really be careful what you plug in and where, right? That update really wants to install. I'll do that probably after I finish the video. So yeah, I mean when chain rule is asked in the problem, right? So obviously it's referring like to plug in 0 pi for s of t, because these are the questions, right? So we want partial s, partial t. So let's set up the derivatives first of all, according to the chain rule. So partial z, partial s first. We're going to do the partial x first, followed by partial s. So the logarithm, so by the way, notice you still have basically, like I said before, the chain rule from calculus 1, right? So how do I differentiate ln of 3x plus y? It's 1 over 3x plus y times the inside with respect to x, which is 3. That was actually a calculus 1 chain rule, so to speak. And then times partial x, partial s. Now I'm going to look at the expression for x, and then partial s of that is going to be just sine of t. Furthermore, we're going to add now the other path, partial z, partial y. Once again, 1 over the radical, 1 over the whatever inside the natural log, right? 1 over 3x plus y times partial y of the inside, which is going to be just 1. The function is 3x plus 2y over here. You write it one more time. So 3x plus 2y. So here is 2y. 1 over 3x plus 2y. Over here is 1 over 3x plus 2y. Partial y of that is 2. And then dy ds, or partial y partial s, which is minus t sine of s. Like that. So let's write it one more time. 3 over 3x plus 2y sine of t. It's better to emphasize the partial x, partial y, because this will be repeated on the next step, right? And then 3x plus 2y, and then minus t sine of s. Okay, let's continue now with partial z, partial t. Let's do it directly. That's going to be dz dx, or partial z, partial x, which is already computed. I'm going to copy it here. But now it's times partial x, partial t, which is s cosine of t. Partial z, y, 2 over 3x plus 2y, followed by partial y, partial s, which is t, sorry, which is 1 times cosine of s. Alright, so now we can plug in the values again carefully, because we plug in 0t, 0 pi for s and t. Let's see the corresponding values for x. If s is 0, obviously x is 0. And then if for y, we plug in pi cosine of 0, which is pi. So we're going to plug in 0 for x, pi for y. So at the point in question, 0 pi, my partial derivatives are 3 over 3 times 0 plus 2 times pi sine of t, which is pi, 2 over 3 times 0, 2 times pi, minus pi sine of 0. So actually this is just 0, right? Because sine of pi is 0. Sine of 0 is 0, so this is going to be 0. And the other partial derivative, we're going to again copy the partials here with respect to x and y, because those are the same. So that's going to be 3 over 2 pi. But now in the parentheses I have s, which is 0 times cosine of pi, plus 2 over 2 pi, but now times 1 times cosine of s, that's cosine of 0, which is 1 in the end, right? This is still 0, goes away. Cosine of 0 is 1, so this is 2 over 2 pi, which is just 1 over pi, the other partial derivative. So I want to conclude with another example. This is actually in the homework, but I'll do just one component of it and you'll do the rest of it. And this is relevant especially from tables when you have not the entire function, but you have basically some values of the function and all of its maybe partial derivatives. You can still use the chain rule. It's just a matter of picking, setting up the correct rule and plugging in the quantities in the right position. So here's what I'm talking about. So in this problem, you have basically some unspecified functions. It tells you that you have a function r of s of t, which is just another function big G of u of s of t, v of s of t. So if I look carefully here, it looks like you have G on the top, which depends on u and v, and then in turn u and v depend on s and t. And notice that r of s of t is just another renotation of the composition. You could, for example, if the problem, let me put it this way, the question here in the problem is to find partial s and t for r. So that partial, and by the way, let's actually use the index notation for a change. Partial s, partial t, right? You could also use big G, right? It doesn't matter. That's interchangeable at this point, right? So it's just basically another name for the composition of G with u as a function of s of t. So anyway, in the question, in the problem, you're asked to compute actually partial s of r at the point 1, 2, rs at 1, 2, and then rt, partial t that is, at 1, 2, knowing the following values. So you have a bunch of values now given to you. You are given us, that's partial s at the point in question, to be 4. ut at the same point minus 3. v at 1, 2 is given to be 7. U at 1, 2 is 5. Vs at 1, 2 is 2. Vt, partial t of v at 1, 2 is 6. Then we have big G, partial u at the values 5 and 7 to be 9. And then partial v of g at the point 5, 7 is given to be minus 2. It's just, this actually looks uglier than it is in reality, but it's just practice with the setup of the chain rule. So again, just for a change, let's use partial notation. So looking now at the dependence of G with U, V, and S and T, right? So RS via G, right? You can, like I said, you can replace with G. How do you do partial S of G? Well, I'm going to do partial U first, followed by U partial S, plus GV times VS. But again, to make it clear, what we're talking about really here is that, and this is where actually it can be, where we have to be a little bit picky here, right? What we're talking about is that GU is again a function of u and v, which is to be evaluated at the point in question, 1, 2 for v, right, at the point for 1, 2 for s and t, right? So remember, we have to compute eventually rs at the point 1, 2. So again, you differentiate first, and now you basically plug in the point, right? So, you know, what you have here basically is rs at the point 1, 2. So that's gu at uv, which in turn are evaluated at 1, 2, times us, again at the point 1, 2. And then plus the other branch, g partial v at u and v, each of them evaluated at 1 and 2, times v partial s, again evaluated at 1, 2. And I was note, obviously the problem gives you the values that you need to compute this. So starting from the inside out, this guy us at 1, 2 is given in the list of these values. That's going to be 4. Vs at 1, 2 is given to be 2. U at 1, 2 and v is going to be 5 and 7, which is the reason you have partial g's at 5 and 7, right? Obviously. Okay, so let's do it one step at a time. So now this composition is going to be partial u of g at 5, 7 times 4 plus partial v at 5, 7 times 2. And now again, we're looking at the values given in the table, in the list here. This is to be given to be 9, and this is minus 2. So that's 36 minus 4, which is 32. Okay, so do yourself the other partial, RT at 1, 2. Follow the same steps, and you should end up with minus 39. So I think that's enough for the chain rule of a function of several variables. Sorry for that update notification. I'll do that now. And we'll continue next time with the next lesson.